example, alpha is 2R. Each xi is in Rd and each yi is in R.
Me too. Yeah, it's okay. So we are given a set of points as the data set. Yeah, it's okay. So we are given a set of points as the data set. Each xi is a vector in Rd and each yi is a real value. We have also a set of models which are parameterized by alpha, and we are interested to find a model which fits the data the best. Given a set of points as the, so we need a measure to distinguish the models based on that measure. Which one is better comparing to another? So you can think of a loss function. I'm going to call it L, which a function of x, y, and m are to distinguish the models based on that measure. Which one is better compared to another? So you can think of a loss function. I'm going to call this L, which a function of x. Okay, got it. So we have a function L, which is called normally the cost function or the error function. It's a function of x, y, and the model. It's penalize the mismatch between the predicted label and the ground truth label. So we are interested to minimize this loss function and find alpha for which we have the minimum. So we are interested to solve the argument of this loss function. You can think of this loss function just now. You can think of the SSE function, the sum of squared error. You have seen that function already, but it is. I'm going to at first speak in more general paradigm, and then I will focus only on the specific example to go through the details. Just now, you can think of a function which is penalizing the mismatch between the prediction by the model and the ground truth given by the data sets. So you can think that x and y here are fixed because we are given x and y. The only parameter for that function that can change is the model, and also the model itself is a function of the parameter alpha. So you can think of that as a function of alpha. So you have a optimization problem like this. We are interested to solve the argument of L of f of alpha for alpha in R. Now it should remind you the gradient descent algorithm. So if you remember, in gradient descent algorithm, we have this situation. We were trying to minimize a function. So you can see this paradigm can be solved just by using the gradient descent, because I need to solve this optimization problem, and this optimization problem can be solved using gradient descent. So, any question? Okay. So let's focus on a simple example. I'm going to solve the polynomial regression, and at first I'm going to remind you the setting. So again, we are given x and y, the set of data points, which are x1, y1 up to x and yn. In this case, I'm assuming that each xi is in R. It means that value setting the b is 1. And also, like always, we have each label is also in R. I'm going to consider the polynomial regression when the degree is 2. It means that each xi is going to be expanded to the vector of 1 xi squared. The model, the alpha is just alpha 0, alpha 1, and alpha 2, which is a vector in R3. And the model for each xi is just alpha 0 plus alpha 1 xi plus alpha 2 xi squared. So, and this model, we need to find the argmin. Okay, let's remind you the SSE function, which have x, y, m of alpha. It is just the summation over I from 1 to n, m alpha xi minus yi squared. Okay. So to solve the polynomial regression with the degree 2, I need to find the argmin of this function. So, as I said, this function is indeed a function of alpha. It's a function of alpha because x, y are fixed. The model is only depending on alpha. So I can think of a function of just alpha. And so I can write it as this. It is the dot product between alpha squared, which is alpha 0 plus alpha 1 xi plus alpha 2 xi squared. Okay. So my f here is the sum of fi of alpha I from 1 to n. Each fi is the dot product. Sorry, it is m of alpha xi minus yi squared. So I'm interested in finding the argmin of f of alpha for alpha in R3. Yeah. Yeah.
The sum of squared errors is yi minus the model.
Okay.
Is there a difference between the written and?
No. No. You can think that if I swap m of alpha with yi, it's the same as just multiplying this equation inside the equation by a minus. Yeah. And since you are considering the square, that would be the same. So they are both the same. But for our purpose, it's a bit better right now to write it like this. So it's the same as so. Any other question? So I want to find the argmin of f over alpha, and I can just call it alpha star. So let's remind you that the gradient algorithm okay, if I want to use the algorithm, the gradient descent algorithm, I need. Can anyone tell me what I need to compute to use the gradient descent algorithm? Yeah, exactly. I need to compute the gradient of f if I want to use the gradient descent algorithm. So let me quickly remind you the algorithm. The algorithm starts with alpha 0 to be alpha star. It could be anything. You can initiate it with a random guess, or you can just set it as the origin. Then we are going to repeat some steps. The next alpha is the previous alpha minus the learning rate times the gradient of alpha in the previous parameter alpha. And then we do these steps until some stopping criteria is satisfied. So you can see I need to compute the gradient of f. So I'm going to focus on computing the gradient in this case. So if I want to analyze the algorithm, I have to compute the gradient of f. So let me copy this. I start with the case that n is 1, just for simplicity. So I have only one data point, x1, y1, and also f of alpha here is just m of alpha x1 minus y1 squared. I want to compute the gradient of f in this case, and then I'm going to deal with the general case with the summation over I. So the gradient of f. Just to remind you, the gradient of f, and I want to make sure that we are at the same page. Alpha here is a vector in R3, alpha 0, alpha 1, alpha 2. And the gradient of f is the partial derivative of f with respect to alpha 0, the partial derivative of f with respect to alpha 1, and the partial derivative of f with respect to alpha 2. So pay attention that the gradient is not a scalar, it's a vector. I need to compute three things: the partial derivative with respect to alpha 0, with respect to alpha 1, and with respect to alpha 2. So the partial derivative of f with respect to alpha 0. If, of course, you can remember from the calculus that I want to compute the derivative, I can just first take care of the power 2 and then compute the derivative inside the parentheses. So it's 2 times m of alpha xi minus yi, the partial derivative of m of alpha xi minus yi with respect to alpha 0. Just we have 1 to x1. Yeah. Can anyone tell me what's the answer for this part?
Zero, because the partial derivative is constant zero.
It's not a constant.
Wait, is it for alpha one or zero?
Alpha 0 with respect to alpha 0.
Zero?
You have 1 here.
Oh, so just one?
Yeah. That's exactly. So it's 1.
Also, x1 is treated as a constant.
Yeah, here. Okay. Here, alpha 0, in this case, the only parameter that matters is alpha 0, because we are going to compute the derivative with respect to alpha 0. Anything else is considered as a constant. So the derivative is exactly 1. So it is 2 times m alpha x1 minus y1 times 1. So what's the derivative with respect to alpha 1? We have the same, but the only thing that is going to change, it is going to be with respect to alpha 1. So I'm not going to repeat everything, just I'm going to write it. So, and what's the result here? What should I write? Yeah, exactly. And I can do the same, and then the derivative of this function with respect to alpha 2 is this constant times this scalar times x1 to the power 2. So the gradient of f is 2 times m alpha x1 minus y1 times 1 x1 squared. Yeah. Yeah. I didn't write it, but you can compute it as well, that the derivative with respect to alpha 2 of f is 2 times m alpha x1 minus y1 x1 squared. Okay, so we have computed the gradient. Just again, note that this term is appeared in every partial derivative. So I can factor it out and put it just as a scalar before the vector 1xi squared. You can see it that it's a constant. It's fixed. It depends on xi. It does not depend on the alpha. The only part that depends on alpha is this part. And also you can see that part is indeed the residual error. So your gradient depends on the residual error. If the residual error is too small, then the norm of the gradient is too small. We agree? So if I apply the gradient descent, I am going to update alpha. The alpha nu is the alpha old minus the learning rate times 2m of alpha x1 minus y1 times 1 xi x1 squared. And if the model is doing good, it means that the residual error is small. And then you should expect that the update is also negligible. It means that it's a kind of self-adjusting. because when the model is doing good, the update is negligible. You can think that if the model is fitting good, is a good model, then you have found alpha, because it does not apply any change on the alpha. As long as the model is doing good, it means that this part is too small. So you are subtracting a very small vector from the old vector. So you should expect that the new one is almost the same as the old one. And in the best case, you can think that the model is doing perfect. It means that the residual error is 0. So the new alpha is the same as the old one.
So just make sure, is that model alpha of x1 or xi?
In this case, I'm just considering that I have only one data point.
Oh, okay.
Yeah. So it's x1. Okay. Just to remind you, n is 1 here, the number of points. So it was about the case that the number of points is 1. So let's get back the general case when the number of points could be greater than 1. So let's assume that n is something bigger than 1. In this case, the f of alpha is just the sum of f of alpha, fi alpha of I from 1 to n. And just to remind you, fi of alpha is just m of alpha xi minus yi to the square. So here, it's a general case, and the number of points is not 1, it's bigger than 1. So again, if I want to apply the gradient descent, I need to compute the gradient of this function. Since the function is decomposable, computing the gradient is not difficult, because I can push. I want to compute the gradient of f. It is just the gradient of fi. I can push the gradient inside the summation, because the gradient is a linear operator, just like the derivative. When you want to compute the derivative of sum of two functions, you compute the derivative of each of them and then do the sum. Here we have the same. So I can do just this. And we have already computed the gradient of each fi. We know that the gradient of each fi is 2m alpha xi minus yi times 1 xi xi. It's exactly the same as what I did for the case that I have only one data point. That was for x1. I can do the same for each xi. So the gradient is this. So the gradient of f of alpha is the summation of 2 times m xi from 1 to n. Okay. Just note that I'm not allowed to bring this part out of the summation because it depends on I. So if I want to use the gradient descent, I have everything that I need. I need the, yeah,
Does the leftmost vector increase in size if our number of alphas also increases? Sorry, right. So the one xi squared, does that increase if you have more alphas?
okay. I could you repeat your question?
One xi squared, will that increase to one xi squared, xi cubed if you were to have more alphas?
You mean if the degree of the polynomial, yeah, if you have if you are going to solve the polynomial regression with degree 3, then yeah, you are right. It is 1 xi squared xi to the power 3. Yeah.
But that doesn't mean that alpha, there's a number of alphas that increases, it's just the number of x.
The dimension of the alpha is exactly is going to increase. In that case, alpha would be alpha 0, alpha 1, alpha 2, and alpha 3. Just note that I need to compute m of alpha xi, which is the dot product between alpha 1 xi squared. So alpha should be a vector with the same size as 1 xi squared. In this case, it's 3. For the case that the p is 3, then it's a vector of dimension 4. Okay. So, okay. If we want to have some guarantee for the gradient descent to converge to the global minimum, we need convexity. And if we want a fast convergence, then we need a strong convexity. So I'm going to speak about the convexity of the loss function to see if it is convex and then try to see if it is strongly convex. So just to remind you once again, f of alpha is the sum of, okay. Again, I'm going to consider a simpler case because I need to draw something and I'm able to do that in the 3D space at most. So I have to consider a simpler case. I'm going to focus on the simple linear regression. It means that here p is 1. So my last function, f of alpha, which is the sum of f of fi of alpha, in this case is m of alpha xi minus yi squared again. And it is plus alpha 1 xi minus yi squared. This is f. Fi. We know that if we have a summation of convex function, then the summation is convex. So if I prove that each of fi is convex, then I can conclude that the f of alpha is convex. So if each fi is convex, then I can conclude that the sum of fi is also convex. So I'm going to focus on exactly one f and analyze the convexity of one f, and then I can conclude if I would be able to prove that F1 is convex, then I can do the same for each of Fi's, and then I can conclude that the F is convex. Let's do it through a geometric approach. Assume that this is alpha 0, this is alpha 1, and this is f of alpha. Just consider a line. Okay, let's get back here. Can anyone tell me what's the minimum possible value for Fi? Yes. It cannot be negative because it's a square root of something. So the minimum possible is 0. And you can see the Fi of alpha is 0 if and only if alpha 1 plus alpha 0 plus alpha 1 xi minus yi is 0. And I can rewrite it as alpha 0, alpha 1, y1 alpha xi. Okay. Okay, so let's bring you to the next page. Can anyone tell me that equation is going to, what's that equation in this space? Just you should be careful that x1 and y1 are fixed, and the parameters here are alpha 0 and alpha 1, and we are just in the space of alpha 0 and alpha 1. What that equation means? Any guess?
Maybe it's like a plane.
It's a line. Yeah, exactly. It's a line. Okay, maybe because I'm using a different variable, it's not familiar for you, but it is just y equals.
So this is the solution space for a single point.
Somehow, yeah, we will go through that.
These are the linear combinations of alpha and alpha 1 that makes this true.
Yeah, it's a linear combination of alpha 0 and alpha 1, but it's going to be a fixed number, so it's a line. Yeah. And that space, it's a line. Okay, this line corresponds to the points that f of f1 of alpha is 0. Yeah, because I solved f of f1 of alpha to be 0, and then I concluded that that's the solution space for that for this equation. So it means that any point on this line is going to make it 0. If I deviate from this line, then it means that f of alpha is not 0. It means that this equation is not. This is not an equation. So it means that you have a residual error. So and in f, it's just m of alpha x1 minus y1 to the square. So you have the square root of the residual. It means that you have something like this here. Okay, just if you deviate from the line, then it increases the Fi with the square root of the residual error. So it's a problem when you deviate from the line. It's like a problem. So you have something like this. Okay, Now I want to, you should think of a surface like this. It's stretched along the line, but in each direction, you can see a parabola or a quadratic function at least. So I want to prove that this function is convex. To do that, I should pick 2 points on this surface and prove that the segment between 2 points is going to be above or at least on the surface. Just if I choose 2 points, for example, here, you can see that purple line is above the surface. If I choose 2 points, for example, one here and one here, you can see the same. And even if I choose 2 points on the bottom line, is also true. For the bottom line, you should think of that is exactly on, it's equal to the bottom line. It's not about, it's equal. But in the convexity, we need to prove that any segment between 2 points are greater or equal to the value of the function. So it's a convex function. Any question? Okay, let me. Okay, you can see the shape of the function here. It's something like this. And this is the line at the bottom. And from this picture, you should be, it should be clear that it's a convex function. Okay. Okay, it's convex, but it was better if it was strongly convex. My question is that, is it strongly convex? Okay, it's not strongly convex. If you want to think about strongly convex, you need a parabola which is below this surface, but this is not possible because you have a linear function along the line, and any quadratic function finally goes above that linear function. So you cannot find a parabola which is a lower bound for this function. It means that this function is not strongly convex. Okay, but there is still one hope. We only consider one data point, and we prove that for that data point, fi of alpha is convex. So we know that the f is convex because f is the summation of some convex function. But okay, maybe if we add 2 of them, then it's strongly convex. So and this is the case. I'm going to prove that if I consider one more f and add it to this, then it is strongly convex. So to see that, just assume that I have one other point, which is corresponding to another line, y2 minus alpha 1 x2. And I can do the same. I have some parabolas in this side. Now, for any direction, even the bottom line, the other point makes it nonlinear, because on that direction, the other one is not linear. So you have a summation of a linear function with a quadratic function, and the summation is, of course, a quadratic function. So it means that the summation of these two is not is a strongly convex. We can see that. Okay. Here, if I add one more term, what's wrong?
then you have two.
Yes. Then it's strongly convex. Now you can have a problem bounding this surface from the below. So it seems that everything is nice. So we have proved that the summation of F is strongly convex if n is at least 2. Of course, maybe one can ask this question: what if the 2 points are the same? The first data point and the second are the same. So indeed, we have only 1 point. Yeah, I need to be careful. It's for the case that the points are not non-general. It means that in this case they are different. For the bigger dimension, it means that for example in the 3D dimension they are not on a line. They are going to produce a hyperplane. In the 4th dimension, it means that they are not in a hyperplane. They are going to, and I can say that generally they should be affinely independent, but you can just that's a completely rare case. You shouldn't be worried about that case. So I can, if at least 2 points are not non-general, I can repeat this statement in a more general setting. It means that if the number of parameters if the number of points is at least the number of parameters, then F is strongly convex.
We have a question in the chat. Is there a difference between strongly and strictly convex?
Yes. They are not the same. Strictly convex, strongly convex is strictly convex, but strictly convex could be, it's possible that strictly convex not to be strongly convex. Okay, if then F is strongly convex, again, I should say that the points should not be non-general. Okay. So everything seems perfect. We have a optimization problem. We can solve the problem using gradient descent. The function is strongly convex. It means that we should expect extremely fast convergence. Maybe 10 or at most 20 steps is enough. But there is a downside for this problem. Okay. To compute the gradient, I need to go through the whole data set. I need to compute the summation from 1 to n. So I need to go through all the points. And if the number of points is huge, then it could be problematic. Just assume that the number of points is 100 million. So if you want to compute the gradient, it is expensive to do that. Even in the case that we are dealing with a strongly convex, still that part could be problematic. So is there any way to go around this problem, to some way to solve this problem? Yes, there is, but there is no free lunch. I have to sacrifice something. And in this case, I have to sacrifice the precision. So I'm going to introduce two variants of the gradient descent, which solves this problem, but we have to sacrifice, as I told you, the precision. Okay. We can have a break for maybe 5 minutes. Okay, let's get back to the lecture. So I'm going to introduce two variants of gradient descent. The first one is called incremental gradient descent. It's a simple algorithm. Again, we initiate alpha 0 to alpha start. Then we are going to repeat some steps. K plus 1 to be just alpha k minus gamma f. The gradient I keep the consistency. I plus 1 until gradient of f is less than some. Yeah. It's an algorithm. You can see that in this algorithm, I'm not going to compute the whole gradient. I'm just considering one of the fi's in each step and compute the gradient of that fi. So, I mean, I don't have to go through the all data points. It's much simpler task to do. And also, we should be careful about the stopping criteria here. Just assume that one of fi's is doing perfect on the corresponding data points. It means that the residual error is 0. So the gradient is 0. So the norm of gradient is 0. So its stopping criteria is satisfied. Even at the first step with doing any update, it means that this is not a good stopping criteria. Maybe it would be better to consider the average of some consecutive steps up to the this step. Okay, and I should be more careful. It should be computed the mod n, because we have I from 1 to n. So the n plus 1 should be considered as 1 again. Okay, and maybe average of gradient of fi for some iteration is at most t. Okay, it's a bit difficult to analyze this algorithm, but there is a variant of this which is called stochastic gradient descent, and that's easier to analyze and see why it's going to work. Yes.
What's the last word after for some?
Iteration. Okay, so it's a simple algorithm. It's in practice, it's working pretty good. Okay, sorry. That was unexpected. Yes. stochastic gradients. Initialize alpha 0 to be alpha start. And then repeat. Randomly choose I from 1 to n. Do the updates alpha k plus 1 to be alpha k minus gamma gradient of f of I, and then k, and then until the gradient of f. Again, I should repeat the same problem here. So what's the difference between this algorithm and the previous one? And the previous algorithm, we start from the first data point, going through the data points, and maybe again, they start from the beginning and doing this iteration until the stopping criteria is satisfied. But in this algorithm, we randomly choose one data point, compute the gradient with respect to that data point, do the update, and again, choose another one. I should mention that randomly, it's going with replacements. It means that the first one and the second one could be the same data points. Okay. So, but I should mention that in practice, the previous one is doing the good job. But the stochastic gradient descent, I can prove that it converges. It's with high probability it is going to converge to the almost the same solution as the gradient descent. So you can see that it's cheaper because in this part I do not have to compute the gradient for the f. I just compute for one of parts fi, so it's much cheaper. So let's let's analyze the correctness of this algorithm. Okay. Just let's think about the gradient of f, which is the summation of if I put 1 over n here and just work with this one, it does not matter because it's a constant, and that constant could be digested with gamma. It means that, okay, I just to take care of that constant in the gradient descent, I can choose another gamma, and then it's the same. Just let's get back to the gradient descent. And yes, if I put 1 over n here, it means that I have something like this. So it is another, because n is a constant. So they are the same algorithm. If someone used this, the previous one, and some other one used with 1 over n, it means that they are just working with different gammas. Okay, is it clear? Okay. Can someone tell me what's the expectation of if I choose I randomly and uniformly from 1 to n? what's the expectation of the gradient of fi if I choose I randomly and uniformly from the set 1 up to n? No, the expectation. If you have some numbers and you choose one of them at random with replacement with the same chance, what's the expectation? The average, yeah. So it's the gradient of f alpha. So the expectation is the gradient of f of alpha. So you can think of each of f of fi as a noisy estimation of the expectation, because you have a random variable, you have the expectation. Each observation of the random variable is a noisy estimation of the expectation. So here I am working with the gradient descent, but a noisy observation of that. It's a noisy observation of the gradient of f. If you think of the gradient of f in this way, then each of fi is a noisy observation of the true gradient, and it's unbiased estimator. So here, instead of working directly with the gradient, I'm working with a noisy estimation of that value. So it should give you a sense that why it's going to work. You see a picture. Just assume that this is the minimum. With the gradient descent, you start from this point, for example, that you somehow continue directly to the minimum. But with stochastic, if you, for example, start from here, you might go there, you might go there. And maybe you do something like this here. In each step, you are not approaching to the minimum directly, because you are computing the gradient, a noisy gradient. So it could be not completely a right direction, and maybe completely wrong for some of the points. It's possible at some point you go completely back, but in average, you are approaching to the minimum. And I should mention that it's possible that when you are very close to the minimum, just you do something like just you iterating, going at some direction, and you never reach the true minimum. It should be considered as a negative point, but somehow it's not bad. It's good, because the true minimum could cause overfitting for the model, but some points near the minimum, it's avoiding overfitting. Yeah.
So as I understand, you find the gradient for certain points and you go in that direction, rather than find the gradient that's higher than one.
Yeah.
Okay.
Yes. Okay. Any question?
But is it always uniform for how you choose your end?
Yeah, it's always uniform. You can think of, you are given the data point, okay, and there is a distribution behind the generation of that data point. You are not aware of that. If you choose random uniformly from that data point, it can be prove that you are choosing from that, you are generating the data from the distribution that the points is generated, just if you choose random. If there is more chance for someone, it means for some points, it means that they are repeated more than one time in the data set. So if you just consider
So the weight of the data set is already preserved by using random, by using uniform.
Yeah.
Okay.
Okay. We can stop here. Any other question?